All right, that should be good. All right, I'm officially recording. As I understand, that's something I have to tell everyone, right? But yeah, I just started it up. So yeah, let's does anyone have any questions before we dive in? Well, we would give everyone about 5 more minutes to show up.
So what exactly are we going to cover again?
All right, so what we're actually going to cover are the steps of creating a URDF file, which is the way to represent a robot on a virtual environment. Right, that's the file that gets used when simulating with physics within a computer. So it's just a standard file used across robotics with different software. It's just a format of a robot in the virtual place. So we're going to go through the process of building one of those.
Yeah, and then in layman's terms, just for people with a little bit less, less time talking about this kind of stuff, what it basically is like a file format where, like you have Word file format, you have docx for a Word document, you have PDF for a PDF document. This is .zacro or .urdf for a robot document. So it's a document that will actually programmatically explain to the system how your robot's put together. There's a rectangular chassis here. There's a wheel here at these coordinates. There's a wheel here. It rotates around this axis. That's pretty much what it is.
Is there
and then,
any
of course, that'll. Oh, go on. Sorry.
Yeah, I just wanted to ask, is there any minimum specs that we need to run this sort of thing on our computers, or should it basically anything be good?
You're gonna want to. The first thing we're gonna do when you're in your setup, our first tutorial is to dual boot Ubuntu onto your system. I would assume you have a Windows computer, correct?
Yeah, I have a Windows computer.
Perfect.
I've been actually wanting to dual boot a Linux distribution for a while now, so this is perfect. I'll be sure to set that up once I get a chance to.
Perfect. Yeah, so you already know what this is. So we have the tutorial there just to make absolutely sure you separate your partition correctly and you don't end up having conflicts with what's in your hard drive. So definitely follow that tutorial very specifically. It's not rocket science, but it does have to be done precisely.
Yeah, otherwise you'll brick your system or you'll wipe all your data because of the way that Windows handles things.
There's a lot of other things that can go wrong that aren't really detrimental. Like a lot of times you'll see what's called the grub screen, which is if you do things wrong, your computer will boot and it won't know what you want it to boot. But everything's still there. You just, go on your phone, look it up on Reddit, and someone will have the answer.
It's just frustrating at that point. It's
Exactly. It's so much easier. It's much easier if you just follow that tutorial exactly the way the steps are. You should have no issues at all. And then after that, what you're going to do in the second tutorial is you're going to install ROS2, which is called it's Robot Operating System, but what it really is like a library tool that pretty much it allows you to create a robotics development workspace and do all this really cool stuff with Gazebo, which is the simulation software we're using. And, pretty much, I don't want to get too into it. Everything's in the tutorials. I'll send the links to those right now.
Yeah, because if you're going to follow along with us, the tutorial will walk you through the version of Ubuntu that we're using. And there's a few things that if you can install the same ones, it will make it easier for you to follow along with any future meetings that we have.
That makes sense, yeah. And is there a specific chat or anything that we join afterwards to talk, or is it just this weekly meeting?
I'll tell you what, we have a few different places that we meet. If you'd like, you can send either myself or Raul or Livia an email, and we will get you all that info so you can stay up to date with us. Just for now, these are our two tutorial. I just sent the first one. Now I'm going to send the second one.
You know what? Are you sending it through the chat? Why don't I spin up a GitLab page for
That'd be great. That'd be excellent.
Do you guys want to have a club repo or just any GitLab page? We can make
either way. What do you guys think?
Because we can make. Go ahead, Howard.
No, I was just going to say I don't think it matters as long as we have one central location, right? So.
Okay.
I just put the two tutorial URLs up there. Of course, there is another tutorial. You don't necessarily need it to follow along, but I did make another tutorial where we sort of run through how to create worlds in Gazebo. I've not finished editing that. I want to edit it before we put it up so that, get rid of all the ums and the uhs and the pauses and make it a little easier to listen to. But as soon as I get that up, I'll send that as well. You only need these 2 tutorials, though, to really follow along with us.
Thank you. I got those links pulled up in my browser, and I'll make sure to review those.
Perfect. Yeah, those
And
will
then
go right.
And I'm shooting you an email right now, just so that
You
I
got
have
my
that
email
done.
address?
Oh, I was at Outlook autofills this. I just typed in your name. It was like, "Oop, here it is."
Oh, beautiful. I get my SN. Yeah, you send it to me through SNHU, and I'll make sure you get those links so that we can all stay in the loop. Awesome. What do you guys say we get started?
Let's do it.
Very excited. I'll give the floor to Raul, who will be guiding this tutorial. I guess, Josephine. Raul is a working roboticist. So I'm a robotics recruiter. I'm in the industry, but Raul is like he's like a lead robotics guy. So he really knows how to get into this stuff. Excellent guy to answer our questions, and I can't think of a better person to lead this tutorial. So I'll give the floor to Raul.
All right. Thank you, Andrew. All right, so like I mentioned a little bit ago, right, we're going to walk through the process of creating a URDF file, which stands for Unified Robotics Description Format. And like Andrew explained, it's just a file that has instructions on how to display a specific robot platform. Could be anything, could be an arm, a vehicle, whatever we're designing on a virtual environment, so you can run it on simulations. Why is this important? Because building robots is very expensive. So it is common practice in the industry to design something on the computer first, try to run it through physics simulators in different environments as closely as related to the real world, right? So if we're building a car, we're going to simulate, a street environment so we can run the simulation on there before we decide to actually spend the money on building a physical vehicle or whatever robotic platform we're doing. So that's the whole purpose of this is standard practice. Big part of robotics is simulation. So this is the way we're starting off. But everything we're doing right now will translate 100% to the real world. We're not doing anything that's not going to be different from what's being done in the real work industry. Before we actually start with the process, I want to share my screen and I'm going to show you a couple of pictures. This is something that I started doing at my place of work. Because of this this kind of tutorials that we're following along with the virtualization, I got my team at the office to actually design the physical robot, and it's already actually built. We built 2 of these, one in my California office and one that's going to be shipped to our Texas office, that we're going to get this code after we all progress through it, and we're going to load it into that physical robot. And I'm going to see if I can stream a live feed from it so you guys can see it moving around the actual office that I have in Texas. So it's not super cool looking, but it's going to allow us to eventually add sensors and do a lot of more functional things with it. So let me share my screen really quick here so you guys can take a look at it.
That is going to be so cool. I cannot wait to see that.
Can you guys all see my screen now?
Yes.
All right, so I have two images. It is a base with a differential drive, 2 motor wheels on opposite sides of the base, and then 2 caster wheels in the front 2 corners. Caster wheel is just a basic not powered wheel. It's just to provide stability for the base. And then the drive's going to work with those 2 back wheels, right? So front, backwards motion, so you can calculate turns. And this specific version of the physical robot has already a few sensors added on there. That's something that we're not going to walk through on this tutorial today. We're just going to focus on adding wheels. But if you guys look at the photo, there's a camera right there in the middle of that tower looking structure. That's a depth camera. So that camera doesn't only see things, but it can calculate distance to what it's looking at. So that's very important because later on, as we build through this, there's processes that allow you to map its environment. So the robot can be smarter and know where it's located in its proximity. Now, another sensor that you can see on there is that little cylindrical black shape with a little flag on top of it. The flag is just put on there because I thought it would be funny to put a flag with our company logo on there. But that's cylindrical shape, spins continuously and shoots out lasers. It's called a LiDAR sensor. So what that does is allow us to map a two-dimensional plane of anything around it, right? So as it navigates through whatever environment it's on, there's going to be those lasers bouncing off the wall into it, and it allows us to map like a perimeter of where it's at, right? So that's that in combination with a camera and some algorithms that we can probably cover later on as we advance through some of these classes is going to allow the robot to become smarter, know how to navigate indoors, and that's basically the basis of a lot of the mobility platforms that you see out there. So the same thing that we're going to do here at a basic level gets implemented into cars like Teslas and anything else that you see out there that can autonomously navigate. The other third sensor that we have on this, if you see the little circular things on the corners of the base there, I don't know if you can see my mouse cursor moving around, but these right here are ultrasonic sensors. So what those do is they send out sound waves and then they receive them from the opposite. So you see two circles, one of them sends out audio waves and the other one receives it. And because we know the speed of sound, we can calculate the distance that it takes to bounce off an object. So that allows us to know if we're getting too close to an object, so we can tell it to stop. And it's more for like a safety mechanism. That way, if it's moving around its environment and the camera or the LiDAR sensors or the top are a little too high, we don't want it to miss like somebody's legs or something that's really, really low on the ground. And that's why those sensors are placed there. So that's a little robot there. It seems small and not too complicated, but like I said, building robots are expensive. So what you're looking at right there costs us about $5,000. It adds up really quick.
Of course, that's a lot more than what our platforms will cost, right?
Yeah, there's ways that we can actually build something like this and, a lot smaller than maybe you can do at home. And we're working on maybe getting a list of materials. So whatever we're using for this robot can also be simulated, by yourself at home. So we're working on that. Yeah.
Again, they're much cheaper than 5,000 to do this at home. We're talking about like a Raspberry Pi. This thing, someone was riding on this, right? Like this is a heavy duty piece of machinery. Yeah, right.
I was actually, I got on top of that, and it like moved me around the office environment when we tested out. So that's why this is expensive. It's using somewhat of industrial sized motors, and the battery that this thing powers, same type of battery that controls one of those electric bikes that can go like 60, 70 miles per hour, right? So that's why this is expensive, but we can obviously scale it down and get the same results just in a smaller environment. Like these cameras, this can detect up to like 20 meters, right? Most of the time, you're not going to be working with that, but that's the capability of those sensors. And we can always obviously scale down. Like you can, instead of that camera, you can use a regular webcam. You might have a little bit less functionality, but you can get away with a lot of the same stuff. So, but once we get to sensors and all that kind of stuff, I think you will start having a lot more fun, I think, once you get to that point.
I have a
Josephine,
question. I had a question. Did you just give your robot sonar is like all I want to ask with the supersonic stuff?
Pretty much.
Yeah, that's basically so what it is.
It has sonar, LiDAR, and camera. It sees in like 3 different ways the world.
Yeah, those are like the 3 techniques that you use out there in real life right now. There's not anything really out there. There's something that we call sensor fusion, where you use a combination of different types of data to come up with different ways for robots to see. But other than that, these are the 3 things you use. You use light, sound, and imaging, which is another version of light, I guess. But those are the 3 things. So if you've heard of like thermal cameras is a combination of a few of these things. It just allows us to see the data in a different way, right? Not in the regular RGB spectrum that we see like visually, all the colors and stuff. But yeah, we can probably touch that in a different class. That way we can actually start getting along with this. But hope you guys, once I can get this stream live, maybe I can even figure out a way for you guys to control it somehow, or like to push your code to it. And I think that'll be even cooler, right? But that'll be further along. That's
going to be a pretty awesome resource, Raul.
All right, so wanted to show that. Now, let's get started. So the first thing we're going to do is we feel like instead of working everything from scratch since the beginning, we're going to provide a couple of packages, some files that you can just install on your computer. We'll launch them and you'll have everything that you're supposed to end up with after we finish going through what we're going to do from scratch. So we're going to make sure that you have the completed file. That way we can cut this off at 1 hour, but we'll cover at least enough so you have the understanding of how to build the finished, objective of this class. And then you can just start going in there and maybe kind of like matching, okay, this is what I did, this is what this has, and kind of figure out on your own, more advanced things on there. We'll obviously we'll be available for any questions that you might have, but I think this way we can accomplish more within the time and I go past an hour, we don't have to. So, Andrew, do you have your GitHub link for your repo? That way they can just download that.
Yes, absolutely. Let me send that to the
in the chat.
Let me put that into the chat right now. So what you're going to want to do is you're going to want to go to your home folder. Now I think everyone who's doing this is already aware, but make sure that you don't already have a folder called ROS2_WS in your home folder. So what we're going to do, let me send you guys this commands.
Yeah, so if you guys can see my screen, if you guys already have Ubuntu, I'm in my root directory right now. Yours might look slightly different because your computer and username might be called something else. But if you list the directories, we want to make sure that in here, what you're looking at on your root directory, there's no folder called ROS2_WS. So that's what we're looking for. If you have one, it'd probably be easier right now to just rename it to something else. That way you can download the one we're going to give you guys. We can run the class with that, and then later on you can move things around if you want to. But for the purpose of this class, just make sure that if you have this right now, rename it to something else.
So that clone command is going to be what I put into the chat here. Git clone, and then this URL.git. You put that, you want to do that from your home directory. Make sure you don't do that from like downloads or desktop or something. So you're going to want to do that. After that goes through, you should have a directory in your home called ROS2_WS.
Right now, in case people are following along and they don't have Git installed on their computer, can you provide the URL to that repository so they can just download the workspace?
Right. I think Ubuntu comes with Git, but that is a good point. It might, yeah.
But just in case, that'd probably be the easiest thing once you do get Git. And if you don't have it, you might want to look into getting it because it is a very standard computer program to use to keep track of all your code on any projects, whether you're doing software engineering, robotics, anything that requires some sort of coding. It's a very standard practice to use some sort of Git repository and push all your code on there. But
I put the command up here on the README. I'm just going to leave it there for now, and then later I'll actually edit it and put in what it's actually for. But that's there for now. If anyone needs it, just go to that URL, which I will also share.
Well, it should be the same one that's on the Git command, I guess. Right?
Yeah, just without .git. Yeah, exactly.
Yes. So if you go to that on a web browser, it's going to take you to the GitHub repository where this is located. It's the one that I'm showing on the screen right now. Right. So just in case you don't have Git and you can't pull it with that command, then you can always go to this web page and you're going to download it from here. You're going to click on code and you're going to click on download zip. So if you do that, you should download the folder. It might take just a bit because there is some heavy resources on there, some graphics that might take a little while depending on your internet connection. But once you do that, you extract that. The name that this folder gives you is slightly different. So you might have to rename that. Right there it says ROS2_WS and a little bit more stuff after that. It says -main. That is because within GitHub, it allows you to create branches, which are like different sections or versions of your code. Nothing really too much to know about right now in detail, but just go in there and rename it. So you can just rename the directory to ROS2WS like that.
And if you did that through Git, you wouldn't actually have to do that. But since we did download it through the UI, it comes with the name of of the main repository.
Yeah. All right, so once you have it, just make sure that it's going to be inside your root directory like this. So you drag it over to there if you didn't download it with Git. But if you did download it with Git, then you should be able to click or type in ls, which is to list your directories there, and you should see it now. All right, so once you have that on there, everything should pretty much be installed for you. So if everything works out well, you have the files required to follow this class. We're just going to go through a couple of things. We're going to run some commands. So if you get errors from whoever's logged in right now, Jose, are you following along with this? Or are you just kind of listening in?
No, I'm following along.
Okay. So if you have this repository then downloaded on there, the workspace, go ahead and open this. If you go into that, so you see the into it, we're basically going inside that directory. You should have some of these files, right? That's what the repository should come with: a source folder, a log folder installed, and a build folder. Now, if you haven't worked with ROS packages and don't have much experience with ROS yet, just don't worry about what these really are. These are some files that get created automatically as you use the software. But just want to make sure that you see what you're looking at the screen right now on your own.
So right now, all I
Just
see is
one
the
quick
readme.
update. You should just see SRC at this point, since we have not Qualcomm built.
Exactly.
Okay.
Yeah.
All right. Perfect. So then if you go into the SRC folder, which is the source folder, you should see a few packages on there. Do you see more packages than what I currently have on my screen right there? You should have at least a robot bring up package and my robot description. There might be a few other files in there. Those are not really too important, but you should see at least those two directories.
I actually would recommend getting rid of URDF tutorial, since we're about to put a package in that directory that has the same name. I should have gotten rid of that on the GitHub.
Okay. So if you guys have at least those two, then you should be okay, even if we follow the along. If you try to install that other directory, it might just let you know that you can't do it because there's one that's already named that. But as long as you have these two, you should be fine. Now, in here, inside the source directory, this is where we should probably launch Visual Studio Code or whatever code editor you use, so we can see the code that we're going to be working with. So in order to do that, if you use Visual Studio Code from within the source folder, you can just type in code, space, and a dot. The dot just tells it to open up that application on that directory we're on right now. So when we do that, it will launch the application, and it should show you everything inside the source folder on your left side. Now, this doesn't necessarily have to be from Visual Studio Code, but if you guys follow along, that's probably what you're using. So you should see something like this.
We never actually downloaded Visual Studio. We kind of implied that you need it, but we never actually downloaded it. So anyone in the future who's watching this tutorial, make sure you install VS Code on your Ubuntu system. Just put in VS Code into Google. It'll be almost certainly the first thing that comes up. So Visual Studio Code is this application we're looking at here. Moving on.
All right, so once we're in here, these two packages, let me explain what these are. Packages within ROS, which is the robotic operating system that we're going to be working inside of, they're basically like small computer programs. They all should have a specific function. In this case, the two that we have, it's a robot description. That is the way we call basically every robotic platform that we design for a virtual environment, right? So if we have a battle bot that we're going to be building in the future, right, we're probably going to call it battlebot_description. That's just standard practices. It's like a naming convention. That way, you know, later on, if you have a lot of packages, what that package is supposed to be, right? It's just a description for ROS to understand how to display your robot on the simulation. So that's what we call it that. Now, inside the directory, there's going to be a lot of files that we're going to be working through, and I'll explain what those are as we get to those. But it's important to know that that's what this package is going to do. Contain the description of your robot, so the applications that we're going to use understand how to show it. Now, the other package, the bring up package, as you can see it says my robot bring up, is a set of instructions that's going to allow us to launch specific sections of code and applications on the right sequence, right? So it is very common practice to use the same name of the robot that is going to be launching. As you can see, they both start with my robot. That's just because that's the way I call the robot, my robot. So if you called it BattleBot, then it's probably going to be BattleBot_bringup. It's just, like I said, naming convention, so you don't lose track once you have a lot of files in your directories. This one has what we call a launch file. The launch file, I'm going to pull it up real quick. It's just a set of instructions in order of what applications should be launched to be able to open up the simulation properly. So this is going to launch the specific physics simulator. It's going to launch a specific world that we're going to simulate a robot in. It's going to launch any other applications that we need. And that's what this is. Now we're not going to work through building one of these today, but we provided one already. And that's what we got you guys to download these packages. That way you guys don't have to really understand this in depth yet. As you work through ROS, which is very important in the future, this is something that will be touched on because they're used everywhere. But just wanted you guys to understand what it is now, because we're going to be launching from this file. So I'll close that. And then the next thing that we're going to do is actually launch the application. Let's hope that this is going to give us a good result, because since everybody uses different systems, as long as everybody's followed everything along, it should work. But what we're going to do, if you have the terminal open, we're going to go back to the workspace directory, which should be your ROS2_WS. And then on here, since you only see the SRC folder, right? If you downloaded the package, you're going to run the command colcon build. And I'm going to zoom in on my terminal just in case it's a little difficult to see. But this last command, colcon build, is something that should already be installed on ROS if you followed along with the tutorials. It's a tool that comes with ROS that allows us to make that code that we wrote in the packages executable. Almost like compiling code if you're familiar with compiler languages. Even though the packages that you build might be on something like Python, which is interpreted and doesn't require to compile, ROS does require to make it executable. And that's what colcon build is going to do. So after you run that command, you should get some sort of message like this that is trying to build a package, and you should hopefully get the summary that says that your packages were built successfully. If you type ls to list the directories, now you're probably going to see the build, installed, and log folders like I have on my screen if you didn't have them before. But that means that you actually built those two packages that we gave you guys, and then you're ready to actually execute the command to launch the simulation. So if everything's good up to now and there's no errors, I don't know if you got any errors right now, Jose, if you got to build this out.
We're good so far.
All right, cool. So since we're good so far, now we're going to run the command that's going to launch everything. And we're going to use the bringup package, which is the one that has a launch file that has a set of instructions that I show you right now. And then we're going to tell it to launch everything from there. So I'm going to copy and paste the command on here. If you guys went into the GitHub repository that Andrew provided, on the README file under that, there should be a command on there. So I'm going to pull it up on the screen and go to it so you guys can see where it's at. Let me maximize this here real quick. Under all of this, there's setup instructions. A lot of the things that I'm talking about are going to be on there, and we might add or remove things as we feel like that makes sense. But if you keep on continuing going down, we're gonna see a command on here. And I just realized that I'm gonna get you guys to do something else right now. But important commands is going to be this one right here that says launch Gazebo, and I think it might have been up here as well. Let me see if it's up here.
I assume what you wanted to go over was the bash RC.
Yeah, we're gonna check just to make sure that that's on there. But this command is what we're gonna use next. We're just gonna check a couple of things on your computer just in case. They should already have some of these things on bash RC if they followed along, but some people might be starting from scratch watching this video, so we'll check some of that stuff. But this right here uses the launch file that I showed you guys in a bit. So this will execute everything in order. Let me minimize this, and we're going to check a couple of things first. The first thing, from your screen, it doesn't matter where you're at, you should be able to do gedit. If you already installed gedit, gedit is a text editor that allows you to see text files. We're going to modify a text file that kind of comes with Ubuntu that allows Ubuntu to understand what's installed in its environment to run things. So we're going to do gedit. We're going to use this little tilde sign, which signifies the home directory. And then we're going to type in .bashrc. What that does, or should do, is open up this file. This file is something that Ubuntu gives you. It's like a set of instructions that says, whenever you open up a terminal, which is this command prompt window, what's going to be available for it to use, right? So on here, there's a few things you're gonna have to have on there for sure. If you already installed ROS and you follow the previous videos, you should already have this. If not, you have to source or let the computer know that ROS, and specifically this version, chassis version, is available for it to use. So that's important. The other line, that if you don't have it, you have to source the workspace. If you were using a different workspace before you downloaded the one that we provided to you guys, make sure that this line's on here. As long as you put it on the root directory, which is what you should have done, source the tilde symbol, which signifies our home directory, and then put this afterwards. ROS2 _ ws / install instead of bash. If you guys recall, when we did the colcom build command, there was a few directories that got created. One of them was the install directory. That's telling it to take that into account, that that's going to be on there. So these two lines are necessary. They can be pretty much anywhere on here. I recommend just to put them at the very bottom, just so it doesn't interfere with anything else, because you're going to have a lot of other things like here, like if you see on the screen, there's a bunch of stuff. Don't mess with anything else. Just make sure that those two are there. If there's other things, just go all the way to the very bottom of the file and just, save them on there. Now, there's a couple of other things you're going to have to install.
Just to be
right
clear,
on there.
sorry to interrupt, Raul. Just to be clear, for everyone who might be watching later, those 4 lines, the 2 that Raul just spoke of, and the 2 lines at the bottom, can all be found on the GitHub repository. Link will be in the description. Sorry, Jose.
Yeah,
sorry, Raul. Go on.
Yeah, that's what I was going to go over. These 2 right here also let the computer know where to find different resources. This is what this file is all about, letting know your computer where you can find certain things, right? People can potentially install applications in different ways. So the way we have this set up, if you downloaded our files, these lines should work perfectly for that. But as you understand how ROS behaves and you find maybe your own way of installing different things, as long as you understand what these things do, these lines, then you might have different variations of this. But for our purpose, like Andrew said, if you look at the GitHub repo, you're able to find these on there. You just have to make sure they're on there. These are going to let the computer know where you can find the files that Andrew was able to get for us for the virtual world that we're going to be using. And then the other one, just make sure that he can source some of the plugins that we're going to be using in the future. So just make sure you have these. I hope the screen, everything's big enough for everybody to see, but if not, like Andrew said, it's on the GitHub repo on the README.
I'm
So
actually doing things on my side from the UI, so we got a little bit of a bigger screen as well. Yeah.
Okay. Awesome. Yeah. So once you have those,
sorry, one more thing.
Yeah.
A great way. What we're seeing down there, what Raul just said, is absolutely. It's up to you guys to figure out like exactly what all this stuff means. A great way to figure that out would be to put this bash RC file, or maybe these 2 lines, into OpenAI or some AI platform. It'll tell you exactly what each of those is and why each of those commands is there. Great way to take advantage of current AI, and great way to find out. It's one thing to follow our tutorial and just go through everything. It's a whole different thing if you actually know what everything means. ChatGPT can help with that. Just wanted to mention that. You can go on, Raul.
Yeah, so that everything he said is great. It's true. A lot of this is going to be looking at documentation, right? So robotics is very broad. There's a lot of things that you do in robotics. So it's very often you're going to be looking at different resources and researching things. So to understand exactly how this works, yeah, we recommend for you to search it and probably use AI. It's a great tool to find out how some of these things work. But once you have these, just click on save, and then you go ahead and close this. One last thing we're going to do is we're going to close this terminal just to make sure that everything it's fresh when we continue working from here. So after you reopen a new terminal, and this is a very important step, now it looks at the bashrc file that we just finished editing, and it takes those changes into account. If you don't close the terminal and reopen it, it's not going to know. So that's the easiest way to do it. Another thing you can do is you can source that file, the bashrc file. So if you didn't want to close the terminal, you can use this command. And let me zoom into my terminal again. But you can use the word source. You can do the tilde and then bash RC. That would do the exact same thing as closing the terminal and reopening it. But it doesn't take that much time to just close it and pop one up. So whatever feels more comfortable for you, but that would be the same thing. Now I'm going to type in clear, press enter, so it cleans up the terminal for me. And then now that we have this, we should be able to make the application run. We updated the bash RC file. We made sure that we Qualcomm built the packages that we provided. So now we're going to try to launch it. So let's see if this works out. If Jose's following along, I really want to make sure that he is able to run it. So the command that we're going to use for this, I had popped it up on the screen right now. Let me see where the screen's at. Give me a second. It's going to be this command right here. ROS2 launch my robot bring up my robot gazebo.launch XML. So I'm going to put it here on the side. Hopefully this fits on the screen. And I'm going to start typing it out instead of, well, I'll copy and paste it and just launch it, right? So we can copy from here from the GitHub, has a quick copy button. We're going to paste it on there. So if you have this, it should allow you to run it. I'm going to try to run it. And what this is going to do is going to look at the launch file that I showed you guys earlier on Visual Studio Code. And that launch file has the instruction to launch different things. It's going to launch Gazebo, which is the physics simulation software. And it's also going to launch another tool called Arvis, which is a visualization tool to look at the URDF, the robot that we're designing. So I'll press enter, and that's going to launch several things on here. So if you look at the screen, everything pops up automatically. We have this robot here. It's a representation of the robot. And then on the left side, we have the virtual world that we're simulating everything on. Now, this world looks very sad and boring. This is just a demo world that we have there that we were testing with. But if you downloaded the GitHub repo, there is going to be a better world, better looking world that we're going to actually launch from now. I'm going to show you guys how to edit that launch file that we talked about and to choose in which world we're going to be launching from. All right, so if you have this open, then everything's working out pretty well. Jose, were you able to launch that?
Yep, I got it up and running.
Perfect, that's good to hear. Then everything is working fine. I don't think anybody else should have an issue if everything's working. All right, so to close this, you could just close the applications with a little X and everything. But since we launched it from the terminal, you can just do a Control-C for a user interrupt, and that would close everything for you automatically. Anything that the launch file executed, it will just close it for you. That's the way I do it. I feel like it's a cleaner quit type of thing. So if there's anything that loads into memory, by killing that process on the terminal, it kind of cleans and allocates the memory back to the computer. I feel like that's probably the best way to do it. Causes less errors. Okay, so once we have that down,
yeah, sorry.
Yeah,
it gets rid of everything at once, so you don't have to like click out of everything and hope things aren't running in the background. It's all gone. So yeah, easier.
All right, so now we'll go back to Visual Studio Code, and then on here we'll go to the directory that has the bring up package, and on there we're going to have a launch directory, and then we're going to have the my robot Gazebo launch XML file. This is the one that we launched in the previous command. We're just going to edit this file here. There's a few things on here. If you kind of take a look at it in like more scrutinize this file, you'll probably be able to tell what it's doing, right? This top three things, if you've been programming before, you might have seen this let command. This is basically creating a variable that's going to contain a specific path of something, right? So we're storing this in a specific variable name because we're going to use it within these commands down here. If you can see some of these here, we call the variable through some of these lines. So I'm not going to explain how that works, but if you've done some sort of coding, you'll probably be very, very familiar with some of the way some of this is structured. The important thing here, though, is that in these top three variables, we're telling which file we're going to be launching. Okay, so we're going to go through there. These lines right here, I'm going to highlight them for you. And I hope you guys can see this. Let me see if I can zoom in a little bit. Hopefully that looks okay. That highlighted section right there contains the name of the world and the location of that file within the packages that we gave you guys. So if you guys download a different world from somewhere else, as long as you put it inside the worlds directory that's in here, you should be able just to choose any world that you download and execute it with this model. So, you guys can look online. There's a few things that you're going to have to be careful with. There's different versions of software to create these worlds. So if you download a world that you can't execute later, it might be because it was created with a different version of the application you use to create the worlds. In this case, Gazebo, right? So the world that we're going to run right now is called Water World. This is the world that that Andrew created for us, and he walked over in the previous video, in the previous class that we had.
Hold
Yeah.
on. So I don't have the worlds directories. I only have the robot bring it up in the description. Are you running off a different branch?
That'll be inside the robot bring up directory, Jose.
Oh, okay.
Yeah, so if you look inside the bring up, there should be
Okay, I see it. I see it.
4
Sorry.
directories. Yeah. Right. So do you see it inside the worlds directory? Do you have those 3, or which ones do you have?
I have the easy and the water world. Water world easy and water world. Just 2.
Okay. All right. Perfect. So then what we're gonna do is here, whatever it says on there, it might say test world. I'm not sure what your version would say. I think it should be test world. We're just gonna change that name right there for the name of the file that we're gonna launch. And in this case, is water world. Okay. So if you change that, you save the file just like you would any other file. The only trick here is that every single time you make a change on a file that's inside a ROS directory, you typically have to rebuild with Qualcomm build like we did prior, and then we have to resource the package. It's just the way ROS works. We're gonna have to do that very repetitively. Sorry about that. There's some instances where you don't have to if you've already been experienced through ROS, especially if you code in Python. There's ways to kind of get around some of that stuff. But for the most part, it's always it's a good thing to know, right? I still do it every time, even though I probably don't have to do it. Just avoids future issues of forgetting, how to build certain files and things like that. So once you make the change, you save it. We're gonna go back to our terminal. I'm gonna make sure that I am inside the workspace. In this case, is the folder called ROS2_works WS. So we're gonna do that, and once we're in here, that's when we can actually do the Qualcomm build command again. We'll do Qualcomm build. You should have a successful message just like it shows on my screen. And then I'm going to do the source.bashrc. That way we don't have to close the terminal and reopen it. I'm just going to do source tilde bashrc. That should take into account everything that we need to do. So everything should be like locked and loaded basically to be able to launch that command again. So now if we type in that long command that launches the file again, we should see the new world load up in the simulation this time. So we launch this. And this is taking a little longer because it has a lot more resources and things on there. So as you can see, Gazebo loaded, and this time it loads with a completely different world.
If you have trouble loading that world, load the one that's called Water World-Easy. It's missing a lot of the moving components and unfixed components that make this world take a while to load. It also looks like there are some textures missing from this island here. I will fix that. I should have that fixed in the repo before this ends up going on YouTube.
So the issue for me is that it crashed Gazebo.
Okay, I think we have something on the GitHub repository for that. So let me pull this up. That was one of the common issues that we were experiencing as we built this set of instructions for you guys. So if you come on here, we have this at the very end, right? So this is the one. Oh no, this is if you don't load your robot common issues. Okay, so I think this is going to be right here, right? Try to run this command. Do you have the GitHub repo on your screens right now on your computer?
Yeah, I do.
Okay, so if you look through here, you're going to find under common issues, you're going to find this section. Close anything that you might have open from the terminal and then just run this command, copy and paste it to see if it launches. See what that gives you.
Okay.
So this just a little bit of background. This command is pretty much only opening Gazebo to see if it opens without opening the other applications that we're opening with that command.
Let us know if that makes any difference.
Yeah, it crashed again.
Interesting. Okay.
So shutting down it. What is this saying? Error code 14. Include URI homepage robot blah blah. Unable to find URI. Coastways model 2. It's giving me a bunch of errors about some stuff it can't find.
Did
And
you make
then-
apps? Sorry, go on.
Yeah, I was just gonna say if you're getting similar errors to what I have on my screen, a lot of those are just resources like visual resources like meshes, textures, things like that. So a lot of those
Yeah.
errors are not crucial to getting Gazebo open.
Yeah, I'm
So as
only
you can
getting
see-
the FDF, which I know those are the resources, and then it just
Okay.
crashes. It's not giving me a reason why it's shutting down. Let me try to
Okay.
run the easy one. Hold on.
Yeah, try to change
If you're
that
having
first.
issues there, what I would say is check to make absolutely sure your bash RC contains the lines
The lines.
exactly as they appear, and because bash RC issues could definitely be the issue.
Okay.
So just make absolutely sure. And I like to put them all at the ends of the file just so that I remember where they are, because the bash RC file is going to have a lot of other things in it that have to do with other things that you do on your computer that have nothing to do with ROS. So just make sure that you put those all at the bottom so we can keep track of them, and make sure those 4 are there exactly as they appear on the GitHub.
All right. Let me ask you this: if I wanted to do a fresh install, like do fresh Qualcomm, I gotta get rid of the build, the install, and the log folder, right? I just delete those 3, and then I can do a fresh Qualcomm. All right. Let me
Yeah,
try
and
that.
that was going to be the next step, to just do a fresh Qualcomm build, right? But you do need to make sure that those lines are in the bash RC, because
Yeah, I'm
they're
gonna
important
check them
to, yeah, so you can know where to pull these resources from.
Okay.
Now, another thing you can try to check, just in case it might be something with your own system, is to run the command gz space sim. And I'm going to type that on the screen. What that does, it just opens a blank, fresh version of Gazebo, which is the application that's crashing you right now.
Mhm.
So you can do what I have on the screen, gc_sim. Space sim. And if you press enter, it should just launch Gazebo like this. It should open up a window that allows you to choose a world or some sort of environment that comes with them by default. If you get this or the actual simulator just opening up, then at least you know that Gazebo is installed properly in your system, and it might be something to do with the packages or the configurations of the bash RC file.
Yeah, that works. And I was able to run
Okay.
a sim from there.
It's got to be the bash RC if I had to guess. Like I'm like pretty sure it's that.
I'm double checking it right now.
Especially if Cheesy's opening. It's not a Gazebo issue. It's a ROS2 issue. And I have a funny feeling it's a file path issue.
Yeah. Now,
Sorry.
another thing that I wanted to check is to make sure the Arvis directory is being called on the CMake file. That's the last thing we checked. So let's just make sure that that's not the issue. So Jose, can you see my screen?
Yep.
All right, I'm going to close some of these things because I had different terminal processes launched. Let me close this again. You see how I'm getting like all these weird errors? That's because I did not stop the applications from the terminal. So that's what I mean by not a clean close, right? But if you're on here, within the code, if you have Visual Studio Code or whatever other editor you have, go into your, it's going to be inside your robot description package. On there, you're going to have 3 folders. Just confirm to me that you have a launch, an Arvis, and a URDF folder.
I do.
Okay, under that, do you have a CMake list.txt file?
Yes, sir.
Double click on that and make sure that under the installed section, that block of code, sorry, that you have all 3 directories listed. Is the Arvis one missing?
No, they're all there. UDRF, launch, and Arvis.
Arvis.
And then destination share project name.
Yeah, so then everything's should be the way it needs to be. Did you try rebuilding already the Qualcomm build just to see if that fixed the issue?
Not yet. I'm double checking the source opt ROS Jazzy setup bash and source ROS WS install setup bash. So that's correct.
I'll tell you
What
what.
about the last two lines?
Yeah. You
The,
need
the
those.
last
ones.
Okay, hold on.
Yeah, so it's gonna be these.
And
The
for everybody else listening, this is a really important part of the process. So don't zone out. This is like half of what you're going to be doing when you're the robotics developing.
These exports on the very bottom.
okay, yeah, those two I don't have.
Okay.
I have different ones because from the other stuff I was doing. All right, I have to
Okay.
change that.
Yeah, so I
do
would
we have-
comment. I would probably comment those out, the ones that you have, just so you don't lose them. And
Mhm.
then these two lines you can find on the GitHub repo if you
Yep,
look
I
through
got
them in
'em.
here. All right, so just make sure those are there, and then do again a rebuild from scratch. That way it counts on those resources being on there. Either close the terminal and reopen it after you do the Qualcomm build, or source the bash RC file, and then we can try to relaunch Gazebo again.
Okay.
I have a feeling that's probably what was the missing part right there.
Let me make sure it's not duplicated.
And now
Okay.
this process that we're following, this is like a setup process, right? At the very beginning, setting up your environment for development is usually time consuming. This is not something you're going to be doing all the time. Once you have your working computer with the environment that you like and you know everything's working fine for you, then after that it's really just development and iteration of whatever you're working on. But these configurations are not going to be something you're going to have to be working with all the time. So just keep that in mind. That's why sometimes, you know, troubleshooting these issues are not something that comes off the top of our head, because it's not something we don't encounter every time in the real world. It's just something that we might have encountered at the very beginning, and we probably don't see it again for, you know, I don't know, years, or whenever we have to set up a new computer. So that's why we're kind of going through this. It's just a setup.
I guess though, at the same time, like in general, just trying to figure out how to get things done is a pretty important skill to have though, right? Just like, you know, figuring out just how to intuitively think, this is what's going on. It's probably this. It's probably file path. It's probably that I don't have all my directories that I should in my cmake.txt file.
Yeah, and that's why we tried launch Gazebo by itself, right? Without anything on top of it, because we wanted to check first from the very bottom up, okay, is the underlying program running fine or not? That allows us to check whether it's a system issue or something layered on top of it. And you know, that's why we're going through those steps, right? Checking from the very basic to more advanced potential issues.
Okay, I'm good now. It was those two lines.
Nice.
Okay. Yeah, so those two lines, what it was doing is Gazebo didn't know where to pull some of those resources. So those two lines just tell the computer where to find it. That's what it is.
Yep.
All right. So now that you see that, you should see that the world, right? That the huge world that
Yep.
Andrew created for us.
With those creepy
so-
balls floating on top, yes.
All right. So if you're on there, you can see my screen. You have two applications on here. Gazebo, which is the one that has the world, and then this Arvis application. This allows us to see the robot that we're designing. Now, the one you're looking at in the screen right now, it's very funky looking. It shouldn't look like that. The reason it looks like this is because we created this project. Half Andrew worked on it, and I worked on the other one. So there's a couple of lines of references that just make it look weird. But if you go into the world and you actually zoom in to this area where I'm at, I'm zooming in on my screen, you can see that the robot actually looks fine. That's the way it's supposed to look. Oh, let me zoom out again. It's supposed to be just a rectangular base, two wheels on the both sides, and a caster wheel right there in the front, which is just for support, right? So it doesn't fall on the nose. So the way this is going to operate, the two back wheels are going to move either forward or backwards, and then the front one just keeps it stable, you know, so it doesn't fall. So that's what we're going to control. Now, the world should be not moving. You should probably see these boulders up there floating around in the sky. There should be a play button on the bottom left corner of Gazebo. If you play that, it should load all the resources and start simulating. When I press play, you see all those boulders fall and they start going through the world. The idea is that the robot should be able to navigate around there and hopefully not fall into the water and, and completely get lost. But you're gonna see that as soon as I press play, the robot was floating in the air. Now it's actually standing on the piece of grass right there. That's because physics actually started and the robot fell because of gravity, right? Now, on this package that I gave you, we also included something that's called teleoperation keyword controls. This is something that comes with ROS. Is the ability to manipulate controls on robots that use typical control systems like wheels or maybe arms, things like that. The code that we gave you guys already has some of these things set up. It's not something that automatically happens, but we wanted to give you guys these two packages so you can immediately start playing around and moving these robots around. So if you have this world and the robots in the ground after you press play, just like I'm showing on the screen, you can open up another terminal. It has to be a completely different terminal because if you close the one that we have open right now, everything will shut down. So you open up another terminal, or in my case, I'm using a cool tool called Terminator, which allows me to split my terminal windows. As long as you have a second terminal, there's going to be a second command that you're going to launch that's going to open up this teleoperation program that's included, that's going to allow us to control that robot on the screen already. So if I go to the GitHub repository, that's going to be here under run a control node to control the robot, right? So we're going to run this command, is the teleoperation twist keyword command. This is a package that comes pre-installed with ROS2. It's a very common thing to use. And we're just going to copy it. And then we're going to go to the second terminal that we have open, and we're going to paste it. Oops, right-click something else. And then we're going to execute. If you run that, you should see what I'm looking at in the screen. It's going to be a bunch of information on there. Let me see if I can make this a little bit bigger so we can see all the information on there. But the application allows you to use your keyboard and certain keys to operate this platform. So you have to make sure the focus it's on that terminal window. So as you can see, I have this kind of like hanging in the background there. I got to make sure that the focus is on the window that has the teleoperation command running. And now you can use these keyboard commands here, these keys, the U, I, O, J, K, L, M, and then those two open and close brackets. And then also these down here. So there's instructions on the screen that tell you, what to do to be able to manipulate the robot. If I press the letter I, you're going to see on the screen that the robot's going to start moving forward. So I'm going to do that right now. Let me make sure this is selected. Oh, it's actually not moving for me, so I'm not sure why. Let me see if I maybe did the robot get hit by a boulder? I wasn't paying attention, so it could potentially be that it got stuck under the world. Let me relaunch that real quick. Make sure that's not the case.
I actually had that happen to me. I relaunched Teleop and it was good to go.
Okay, so I'm relaunching the world. I'm gonna relaunch Teleop as well after the simulation loads, just to make sure. And then I'm gonna zoom in over here. I'm gonna press play closely here so you guys can see it fall. Once physics get applied, the robot should fall down. There you go. So now I'll run teleop, and now the teleop's running. Oh. It's actually not working for me. Are you guys, Jose, are you following along? Is it working for you or no?
Yep, it's working for me. I'm gonna have some complaints with you guys about game development though, because these commands.
Yeah, so the robot's moving for you.
I'm slowly moving up this ramp. Real slow.
If you press the letter Q a bunch of times, it'll speed it up. But the faster you go, the harder to control it is. That was not on purpose, but it worked out pretty well because now you have, that complexity part of the simulation that if you go too fast, the turning is going to be very difficult. Yeah, you see? So
yeah, I'm upside down now. It's gone.
All right. Let me try to relaunch this because I want to make sure that you guys see it on my screen. I just don't understand why it's not working here. Let me zoom out. Something is acting funny here. I don't know if you guys can see my screen is like launching and pausing really fast at the same time.
Yeah, that's weird. I haven't had that happen. Oh, it's not even playing, or it's playing, but like at a really, pixelated rate.
Yeah, that's why.
Definitely try starting that again. It happens to me like what? Now that I'm really seeing it, it has happened. I just started again. Oh, now I'm having the same thing. Look at this.
Okay, so I'm gonna do Qualcomm build again. This is something that you guys might encounter later on. I mean, it's this kind of stuff's not perfect, and it's open source, right? So it's stuff that's getting updated all the time. But let me do this. Typically, whenever there's issues like this, one of the first things I look at is rebuilding the packages. So what I do is I come to the workspace. In this case, is this ROS2_WS, and you can either do it through the like the actual GUI, right? Which is physically seeing the directories like this. You can go to your home directory, and you can actually just erase these three, delete these. Now when I ls into here, they're no longer there. And then what I'll do is I'll Qualcomm build again. When I do that, it should rebuild everything for me one more time. And I get the successful message. Everything rebuilds, perfectly up here. And then once you have that, you can do a bash. You can do a source, bash rc, just to make sure that it loads the environment again. And I'm going to relaunch Gazebo with the same command just to see if this time it launches better.
We also need a camera view that tracks the robot. I don't know how we can do it in Gazebo. That's something we desperately need.
If I can make this load here, is this the package that has the camera, Andrew, or no?
Which package?
The one that I have on my computer. I don't know which one you uploaded to your GitHub repo.
I'm sorry. I was actually taking care of something on my end. Could you refresh me on the question?
Yeah, Jose was asking about adding a camera sensor to this, and we already have a version of a camera,
Right.
but I don't know.
We
I
do.
don't know if it's this package or not.
So I didn't mean a camera sensor. Hold on. Let me stop this robot.
No, but a camera sensor is a pretty good way to accomplish that, though. I mean,
yeah, but that would be a cool way to do it too. But I meant like Gazebo should have a way for you to have to set up the camera to track the robot itself, so you stay in a view where the robot is within your view while it's moving around.
It's this track feature. Follow, prelook. So you have to right click it. Yeah, you right click it, it'll give you those features on there. Yeah, but we have a version of this robot that actually has a camera in front of it. This model, I don't think has it. If you look at it, the other version that we have has like a rectangular shape here in the front that works as a sensor. And I have that, but I don't have it loaded on here. Now let me look at something on my screen real quick. It's still giving me those issues. For some reason, it just keeps on struggling on there. So I'm gonna change something on the launch file. This one's not launching automatically, so I'm gonna see if by launching automatically everything loads better. But on your end, Jose, you said that it's working, right? You're able to move it and everything?
Yes, sir.
All right, so let me open up the file here, and then under, where is it? Gazebo path. This one. -R. Okay. Yeah, I'm pretty sure it's that one. I'll save it. I'll go back to my terminal. I'm gonna do Qualcomm build. We're gonna do source -rc. I'm gonna launch this one more time.
Sun Coastways. Hey, it's gone. Huh? All right, is it? Because is it the last place I left it? No. So if I reset the sim, does the robot not reload into the world?
How did you reset it?
I reset it in Gazebo.
Okay, so no, it won't because we're using the launch file. What the launch file does is gets all the resources and throws it that way. Yeah.
So I have to relaunch the whole thing.
Yeah, you have to do the full relaunch with the line, the command line that we gave you.
Okay, that's fine.
All right, so let me look at this here real quick. I have this workspace and I have this old workspace. Let me look at something here. Okay, what I'm doing on the screen is just related to my system. I have different versions of the same package that I gave you guys. I feel like there's something on the one that I'm showing you guys right now that I might have accidentally typed, I don't know, something in there that's conflicting with it. So I'm gonna rename that one. And I'm gonna go back to the more advanced version that I created with the camera, just so you guys can see it.
Yeah, I'm not sure what's going on with the camera thing.
Okay. So I'm gonna do this real quick here. All right, what I'm doing on the screen is the exact same steps. I'm just redoing it with this new package, with this new version of the code. All right, so when I launch this, let's see, this gives me a different result.
Wonder why it's glitching like that.
Yeah, not sure why it's glitching, but as you can see, my robot's moving now on the screen. So there's something different on the package that we downloaded that's affecting my system specifically. Maybe a restart of my system will probably fix this. Looks like it might be something with the graphics card that I'm using. I don't know, but you will
Yeah.
encounter things like this eventually because this was not behaving like this earlier today. I just don't want to restart and get cut out of the meeting. But if you look at the screen now, the teleoperation is working. So I can move forward. I can turn right. So this is what Jose was seeing on his screen. I can speed it up and have better results. Hopefully, as you can see, it's going faster now. But it becomes a little more difficult to control. So if you get out of I'm like drifting right there.
Did a wheelie.
Yeah, you see it? Yeah. So the whole point is that this platform that you guys are looking at, and I lost it. I don't know where it went. Oh, it's up there. It's going to be the platform that we're going to be using to compete on a BattleBot style. And I think that's going to be like the differentiator. That way, not everybody can have like a more advantageous position if they make a more stable base. I think this would make it, interesting, right? That you're going to be able to add, extensions to this, like maybe like an arm that pushes your opponent away or something like that. But the base should stay the same. That way, there's that equalizer between everybody that competes. So
okay, so we don't want to change the base, change the sizes of the tires and stuff like that.
no, I think we should keep that the same. Yeah, because I can already see you're thinking about, how to overcome that stuff. But this is going to be interesting because you're going to have to anticipate that this has real physics, right? So you can't put an arm that's too heavy. It takes account weight. It takes account, how long is it? It'll tip over, so you have to kind of like think of those things as well. Now, besides that, once we do get to the point of having those competitions, we're also going to give you a range of force that you can apply to a specific motor, right? We don't want you to like add something to it that can just like launch your opponent, freaking like miles away or anything like that. So we're gonna give you like a certain like constraints to stay in between. That way it's not too unfair, and everybody has that kind of equalizer to make sure that it's fun for everybody.
No fun.
All right, so if you downloaded these packages, right, you have this. Let me check if this one has a camera. I'm not sure if this has a camera or not. Let me just try to show you guys really quick, just in case it does have it. I'm gonna go into Gazebo, and I'm gonna try to launch the camera module just in case it has it. You guys see how this is potentially gonna look in the future. So yeah.
Can we change at least the controls?
I guess we got to think about that because this might make it more. I think it's challenging when it's a keyword like that, but we'll figure it out. If it's too difficult, then maybe we can change it. Like, what do you have? What idea do you have for the controls?
Well, if we can set up, no, I want to know how much customization do we want to just have it so that they can set up, at least for the first one, only modify like what they have attached to the robot, and then everything else is the same, or can we customize everything else other than the base? That was my question.
I think for the base, let's keep it standard, including the controls, right? Anything that you
Okay.
add to it, maybe that can be the differentiator right now. But maybe for the future, we can maybe the final, if this eventually like scales, we have different, like an elimination round type of thing. Maybe the final can be allowed to do something crazier. But I think for now, I think just keeping it like that would be a good idea.
Okay, I'm fine with that.
Absolutely.
All right, I'm gonna try to add the camera real quick. This is something that I thought my version of the robot already had, so we're gonna test real quick. And if it doesn't work, it's because your world does not have the command entered on there. I think I might have removed it. But yeah, so it's not reading the command, but right here you see my screen where the gray area is at. Right there is where you should be able to see the front view. If you see the simulation here now on Arvis, you see that rectangular gray area. That represents a camera sensor.
Okay.
You can see the axis. So anything that's on the view coming this way on the screen, right towards the front of it, that's what we're going to be able to visualize here. So it's going to be a front-facing thing. Allow you, if you have an arm facing forward, that's when that'll probably be useful. So you can see like where it's actually pointing at and stuff like that. But that's the next step that we can probably send you maybe a documentation. It does not take a long time to add something like this. So maybe a small PDF can walk you through the steps and modifying any robot that you already have. All right, so let me go ahead and stop this real quick. And then I'm going to give you one command, Jose. Everybody should follow this command, and it should work unless you have some sort of different customization. But we're going to install a package that not everybody might have by default. This is the URDF tutorial package. What this allows us to do is that when you're building a URDF, a new robot, it allows you to launch Arvis with that robot and visualize what you're building. So you're not writing just code and can't physically see it. It should allow you to just launch it. And then Andrew had a little bit of trouble installing it through a single command, but I was able to do it fine. So I don't know, it might just be the way to install Ubuntu.
I got it with just the git clone commands.
Yeah, so hopefully they don't have to do the git command. Hopefully this other command works perfectly fine, but let's try it out. So I'm gonna show it on the screen right now. I'm gonna show the command. Just give me a second. I'm pulling it up. And this should hopefully work for everybody. So we'll check with you, Jose. If it works for you, then it should work with everybody else.
Okay.
Okay, so I'll follow along. You guys can still see my screen, right?
Yep.
All right, so first let's update all our Ubuntu repositories. So do a sudo apt update. It might ask you for your password.
Oops.
After you enter it, hopefully it doesn't take too long, but it's going to try to update any directories that Ubuntu might require to download different packages. Once you do that, then the next step is to actually download that package. Okay. Now we're using the version Jassy for ROS. So we're going to type in this. It's what I have on the screen. It's going to be sudo apt install ROS /jassy -urdf -launch. Okay.
And got it.
All right. Did that successfully install? Like, did it give you a good results?
Yep.
All right, perfect. So it looks like it's working for you. Now, there's another command that I want you to run, and it's going to be very similar, but instead of putting URDF launch, it's going to be URDF tutorial. So the same command, but instead of launch, so it's going to be the word tutorial. Run that.
Got it.
And all right, so I'm showing on the screen. The only thing that changes is that word. So after you install those, go ahead and do a source that bash rc the way I have it on my screen, just to make sure that everything's reloaded. And then what we're going to try to do now is launch the same URDF file that we provided for you guys. So in order to do that, there's a lengthy command, but what we're going to be doing is launching this package we just installed with the last two commands, and then we're going to tell it which file to launch within it. So we're going to launch Arvis, not Gazebo, but we're going to do that. First, we have to find the directory where the URDF file is located. That's going to be inside your workspace. Then inside of that, we're going to go to the source folder. Inside of that, we got to go to the description package, which is my robot description. And then there's going to be a URDF folder. And then finally, in there, you're going to have all of the different URDF files that you've created. You're probably going to see less on your screen than you see on mine. That's because on mine, I'm already working on adding arms and a few other things that I'm going to teach you guys later on. But the main one that you should have is the one that says myrobot.urdf.sacro.
Got it.
Okay. So if you have that, now there's a special command in Linux that you can type in pwd. When you do that, it gives you the roots or it gives you the exact location of that directory that we need, right? So we're going to make sure you have this directory. We're going to use it in our command, okay? We're going to need that. We're going to need the name of our robot file. And then now the command that we're going to launch, I'm going to paste it on the screen. Let me check to see if it's in our GitHub repo first. Okay, so it's not on here. Let me go ahead and put it on the screen so you guys can have it, and we'll make sure we add it on this on the README file as well. But the one we're going to follow is going to be, give me a second here. Make sure I give you guys the right one. We gotta use the package that we installed. So it's gonna be the URDF tutorial launch display. Okay, let's try to run this command. Let me try to make this a little bit bigger and maybe zoom out a little bit. Can you still see the screen, what I'm typing in there, or is it too small?
No, it's good.
All right, so we're gonna type in ROS2 launch, and then in case you didn't know, once you start typing in a command, you can press tab and it'll help you finish it. So if I start pressing URDF and I press tab, it'll kind of complete it for you. So try to see if you can get to the point that I'm at. ROS2 space launch space URDF tutorial. Then you're gonna put display that launch that py. Let me know if you can tap through that. Did it help you tap through?
Yep.
Okay, so now the next part, this is where we designate which model we want to launch on here. We're going to type in the word model, colon, equals, and then after that, we're going to put that absolute path. We're going to copy this. We're going to paste it there. And then the last part of this command is going to be a slash and then the file name, which in this case is the myrobot URDF sacro. And the same way, you should be able to start typing it out and it should help you complete it. So at the end, you should have all of that. That line, even though it's long and it might seem complicated right now, it's basically saying use ROS2, which is an application that we're working with, and then look inside these two packages. You're going to use the launch package and the URDF tutorial package, which we just downloaded just a few minutes ago. And then we're going to use the display launch file with this model that we created, right? So as we create a new model, we're going to be using this line every single time we want to see changes that we made to it. So if you press enter, this should launch Arvis and allow you to see your robot. And you see how here it looks perfectly fine. It doesn't look all weird like we did when we launched Gazebo.
Yep.
This is what's going to matter. This is what shows you everything on your robot, right? So if you're seeing this on the screen, then you did everything right. Do you see it like that, Jose?
Yep.
All right, perfect. So that is where you want to be. There should be a small little window here on the left side. Do you see that, the joint sync publisher?
Yep, I see it.
All right, this is a cool tool because as you build a URDF or a robot, it's made out of different components, links, joints, and a few other things under that represents the physics and the shape within the simulator. When you add joints, this allows you to simulate how the joint behaves. So as you can see on the screen, if I move this back and forth, it rotates one of those joints. Okay, this is where we test how things are going to behave in a robot. So as you add arms and different joints, this is how we'll know if it's being built correctly. So a lot of the times I've seen people copy a wheel, but you don't realize that when you copy it, you're changing its orientation. So you need it to spin in the opposite direction or vice versa, right?
Okay,
So that's something.
Question: does the blue represent the y-axis, green X, and the red Z?
Yeah. So in my case, I always use I believe I always use blue for X, or
For
X
X?
for the green's the Y for sure. I think for X I use red.
Okay.
And you can change that. It's not, I typically try to orient all my axes the same way because it simplifies the coding for me. But whatever works best for you, as you start building, you get to decide whatever you want. But if you can see, everything looks pretty much standard on my screen. I keep everything facing the same way, so I don't have to remember like, oh wait, that the axis was in a different orientation, or that wheel was looking in a different way. This way makes it easier, at least for me, to always know which way it's oriented. So just my advice to whatever axis you use, just remember your convention. That way you don't get confused whenever you're making changes and stuff like that.
Gotcha.
Yeah, it's okay. So we're going to close this now, and then I'm going to start explaining how the actual URDF is composed. Very easy. I know this took already the hour, so I'm going to go over it. If anybody's here coded in HTML or done any XML type of markup language, that's basically the way a URDF file is composed. There's different tags that represent different things, and then ROS knows how to interpret those tags to be able to load it into these applications. So I'm gonna go ahead and close this terminal thing, and then I'm gonna open up the code, and I'm gonna open up that robot file. Okay, so we're gonna go into the my robot description, which is the package that contains the URDF file. And then inside the URDF folder, we have different files on here. You should have at least the my robot URDF, commons, and mobile-based Gazebo, I believe. Those three files you should have at least. So the one we're going to open up is the one we launched right now, is the my robot.urdf.sacro. Okay, if you have that open, you should see something like this on your screen. Should look somewhat familiar to what an HTML file will look like, right? Opening and closing tags. There's probably going to be a lot of properties within those tags that you might not recognize, but they're not a lot of them, so I don't think it'll be too difficult to understand. Now, there's three main tags that are absolutely necessary for the software to understand that this is a robot file or a URDF. I'm going to open up a second page here. Let me zoom out a little bit of this one. So let me know if this is a little too small. But the main ones are going to be this opening XML tag. So that has to be at the very beginning, okay? And then the other two ones, the other two tags are going to be this robot tag, which is going to be an opening tag, which we'll copy. Oop. And then at the very end, if you're familiar with HTML, you have to close a lot of these tags. It's going to be a closing robot tag. So the difference on a lot of these tags that are open and closed is that the opening tag does not have a slash at the beginning of the name of the tag. So you can see this one just starts with the open bracket, the word robot, This one, to signify that it's closing that section of code, it has this backslash on there. So everything that represents this robot should fall in between those two tags. If you don't have an opening robot and a closing robot tag, it's not going to work. Okay, this XML version 1 is also very important. There might be different versions of XML. Not too fluent on how XML is used everywhere, but you always want to use version 1 because that is the version that Ross is looking for specifically.
No,
Okay,
you don't have to worry about that. The latest version of XML is 1.1. They move up very slow.
Okay, yeah, so that's good to know. I wasn't aware of that, but for some reason, if you put 1.1, it might not work. So just make sure it's 1. I know that that's something that it breaks if you don't have it correctly. Now, you technically don't need this Zacro version right here. So if you were to remove this, it'll still work, but it's going to be more limited. Zacro, it's a word that we threw out earlier today. It's something that Ross uses specifically. I don't know if there's other applications that use Zacro, but what it does is it enables URDF files to have more functionality. For example, using variables within, using macros, creating like functions that you can reutilize throughout the application, or in this case, the URDF. Like think about a robot that's going to have a spider, right? It's going to have several extremities. And you might be able to just copy the exact same structure, right? The leg might be the exact same thing. Why recode it? Why have 6 different versions or 8 different versions of the same code, right? In coding, you want to reutilize whatever you can. That's what Zacro allows for your URDF files. You're able to create one structure and just tell it, reuse it. And if something slightly changes, you can pass parameters or specific things just to that structure. That's what Zacro enables you to do. So I say always use it as long as you're working within ROS, because ROS is not the only thing that you can use out there, right? So there might be other applications, other platforms where you cannot use Zacro. One of them very popular that we use that does not allow Zacro, it's NVIDIA, the NVIDIA platform. Their ecosystem creates their own profile, their own platform. So there's converters. You might have a Zacro file or a URDF. When you load it into their platform, it goes through a conversion tool that they provide that will completely change the format. So that's one of those things that right now in the working environment, we have to have 2 versions of everything. And as we make a version of one, we have to modify it in the other and vice versa. It's a pain. It's very time consuming and problematic, but sometimes that's something that has to be done. And there's a lot of things like that you'll learn over time when you start working more into robotics, but just keep that in mind. URDF works for pretty much anything robotics. Zacro, it's ROS specific, Gazebo specific. Okay?
Okay.
All right. So now, let me cancel this. There's a bunch of other tags on here. The main ones that you're going to have to remember are the link, which is this one right here, a link. And then there's one called a joint. So let me pull a joint, which is down here. All your URDF files are going to be made up of these files, or these tags, I'm sorry. A link would be a physical structure. In this case, if you remember, a robot is made out of a big block, the blue block. That's a link. It's a rectangular prism that we call a link, right? In this case, if we go up here and we look for one of those first links, not the footprint that I copied over, but that first base link, this one right here, this represents that blue block right here on the right side. So this link, I call the base link. That's just the way I like to name it. You can choose whatever name you want on here. My suggestion, whenever you're referring to a link, always use the name link on there, because as you write these things, it will get confusing. We have some robot URDFs that are extensive, so many lines of code, and this allows you to do a control find and find different tags a lot faster. So whenever I'm talking about a link, I always put the word link in the name convention. So since this is a base underscore link, right? Now, within the link, you're going to have different tags. The visual tag, I think it makes kind of sense, is what the user is going to experience visually, right? On the simulator, on Arvis. You have to have that, and within it, there's a few tags that are required. Geometry, which if it makes sense to you guys, it's also the shape that it's going to take. right? In there, you're going to have different rudimentary shapes. There's boxes, there's spheres, there's cones, there's cylinders. And each of those are going to have its own requirements. If you can kind of tell here, you have to pass a length, you have to pass a width, you have to pass a height, right? This right here, these are variables that I am passing along. And maybe I'm explaining this a little bit in a reverse order, but if we move here to the top part of this, of the left application, this is what Sakura allows us to do. We can create variables and things that can be reutilized later, right? So here we're using the base length. As you can see, there's a variable that I created. In this case, they call them properties, but it's the same thing as a variable that's going to contain a value. So if I actually call this at the very beginning, right, inside the robot tag, but at the very beginning, before I actually use that call here, right, then I can use this $sign, and within the what do you call those squiggly brackets? I don't know what you call those. You can use the name of that property that you created, right? So this is good because just like in coding, now you can change standards, right? Like let's say you represent the height of your robot and you use that measurement 1,000 times in your code. Having to find every single one is going to be very problematic. You're most likely going to miss one or another. So by using variables, it allows you to make those changes, right? Not necessary. You could literally just remove this and type in a number, you know, 1.5 or whatever, and it'll work. But I like to use variables. I like to take full advantage of Sacro, so that's what that's for. That's why you see that on there.
It's kind of like
that's it.
Kind of like a header in a C++ project, right? Where you're just kind of putting everything, all the declarations in one document, staying organized so that you don't have to make any changes to the other files if you don't need to.
Yeah. If you have some experience with web design and any other language, you can include files within a file so you can kind of nest them, right? Mm-hmm. That's something that you can do. If you look at the screen on the left side, right here, what I'm highlighting, the file name, I'm including another file that has some sort of information within this file. So if your file is getting too long, you can always break it up into pieces. That's something that Sakura allows you to do as well. So this comments property is going to be something that's going to be utilized from this line coming down. So if you write something above that is dependent on information being found in another file, you won't read it. It'll crash. So you have to make sure, you have to understand that it's followed from top to bottom. Okay. So if you don't declare something, just like when you're coding, you don't declare a variable, you cannot utilize that if it's not declared, right? Because it will give you an error. So the same thing here. You can create a different file, you can include it on there, and then go from there. If you look through this code, which you guys already have, what I like to do, and it's just best practices in my opinion, if I'm going to create a different section of the robot, I create its own URDF file and include it within the main one. So for example, the camera. I have a camera Sacro, right? You can use the word URDF or Sacro interchangeably. You can use it. It understands both of them. I just like to use Sacro in everything that's going to take full advantage of Sacro. But I do use the word URDF in between. So if you look at the name of the file, I called it .urdf, .sacro. That's because originally I wasn't using Sacro. And then I started using some of the features. So I just added the .sacro extension, file extension. But that's what I do. Different sections of the robot, put it in a different file, and then just include it. And you can see those in here. That's why I have different files. That's why that's there. But yeah, that allows us to do it on the right side. So if you have that, you'll be able to see it that way. Now that's geometry, right? That's where we ended up right now in the visual. The origin, right? This is very important. This is how it's going to be visually represented, right? So you have the base length. Where within that base length do you want that shape to appear visually? So it might be slightly confusing until you try it yourself, but when you're building a shape, imagine you have origin as 0, 0, 0, as we're thinking three-dimensional space, right? Mm-hmm. But you want the visual geometry to be slightly offset for some reason. You can modify that here. Okay. The reason I have that here is just because of the way I designed it. I don't recall why I divided the height by 2 on here. As you can see, I'm dividing it by 2, but that was just part of my design process. So as you build your own robot, you modify those those properties, right? Now you see the X, Y, and Z, that's part of it. But then you also have your RP and Y, that's your roll, pitch, and yaw. That's the rotation of those axes. So if you correlate the X axis, the rotation for the X axis is going to be your R. The rotation for your Y is going to be the P, and the rotation for your Z axis is going to be your Y. So in this case, we want it to just be oriented the same way. We don't want to mess with the visual orientation of the shape. And that's what that is right there. And then the material, in this case, I just put blue. If you don't create a material like I did here on the left side, if we go back to here, I have blue. I'm going to copy it and just bring it over. It's another feature that Sacker allows you to do to create different color textures. If you don't have one created, what I have under color, which is a RGBA, which stands for red, green, blue, and alpha, you can just manually enter that on here instead of a name, right? So basically this right here, you would just replace it under the material. And I think actually you wouldn't replace it there. You would have to have an opening and closing material tag. So you would have to have like a material tag, and inside of there have the color tag. That makes sense to you guys. But I always use the material. I always create the materials. I don't bother too much with using like very cool looking meshes, because ultimately the point of the simulation is to make sure the physics work properly, not how cool it's going to look. Gazebo is not really meant for like appearances and making things look amazing. Is to try to figure out the functionality in the real world is going to be as you expected. There's other tools that you can use for rendering to make the animations look amazing. Those are usually software that you have to purchase because they're specialized for those purposes. But you could add meshes. You could have something cool looking, like you saw the 3-dimensional world that we loaded earlier. You can go very extensive on some of those things. Just keep in mind that whenever you run very cool looking things, it might use more resources from your computer. So if you don't have a high-end computer, it might be sluggish. That's the only thing you have to kind of keep in mind. So this will load that material, and that's pretty much it for the visual. The visual only requires those 3 tags. I think you can even get away with no material, no color, but in that case, everything is going to look dull gray, like the default color that it gives you. So those are it. Now for collision, which is the next tag, this is super, super important, because if not, it's just going to float in space, right? You can have all this robotic designs and everything on the simulation, but if you don't give it a collision, it's not going to know that things can go through each other, or what to do with it, basically. Very similar to the geometry, right? It can be, most of the time it's going to be exactly the same. As you can see it, right? It's kind of like a copy almost of the same information, right? You're going to have the geometry, which is going to require a shape. So typically it's the same thing. This usually you can just copy and paste it. There's very, very strange circumstances where you have to make it different, because if the shape looks one way, you want it to interact the same way, right? I've seen where the visual is more complex. For example, let's say I'm simulating a human being, right? A humanoid, and the arm, my arm's it's not exactly a rectangular prism, right? It's cylindrical in some parts that have fingers and things like that. But it might not be necessary for the collision to detect every single finger independently. I might just tell it, hey, you know what? For the collision, detect the full rectangular prism, because you don't need to represent every single shape and curvature of my arm. So that's the only time that I would see that the geometry of the visual is different from the geometry of the collision. Now, from these two, one that's very important to keep as simplistic as possible is the collision geometry. When GPUs process simulation on computers, the resources intensive, or where it sucks more resources from, where it takes it out from, is not the visual. It's actually the calculations that it makes when detecting the geometry on collision. So if the visual mesh, right, the design, the way it visually looks is very complex, that's okay. But if the geometry is very, very complex, that's when it'll slow things down on simulation. So keep that in mind. If you can keep the geometry of the collision more simple, the faster your simulation will run. You can copy that. Now, the origin also, it's pretty much a copy of it. It shouldn't really change. If you're changing it, it has to be a very specific circumstance. For the most part, it's really easy. It's got to be just a copy of it. The important one that I want to talk to you guys about, and I'm not going to go too much into detail, but it's this inertia, right? If you guys have taken physics courses before, this goes into physics. Inertia is how physics interact with planes, right? So if you have a collision shape, how physics are going to interact with it, right? When something bounces off of a curvature, it's going to react differently as it's going to react with a flat plane. So this stuff right here, it's something that you probably, as a designer in robotics, are not going to deal with too much. This is more related to a mechanical engineer. In a real robotics team, usually you divide it into 3 sections. You have your software people, you have your mechanical people, and an electrical team, right? Those are usually the 3 main components. The mechanical guy gets instruction by maybe whoever's leading the team on the design and the purpose of the robotic platform. And then they will design it in specialized CAD software, computer aided design, right? So they'll use something like SolidWorks, but they'll do the full schematics. They'll have like detailed measurements and things like that. Usually they export some sort of version of a URDF, which you as a software engineer within robotics probably has to modify slightly. It's never perfect, right? There's different softwares, they're all exported in different ways. But what is always the same is that they can export the inertia values for a specific CAD design. So that's something you're probably going to default to asking them. If they're going to design it for you, their software will give you how physics should interact within that shape that's been calculated. That's what that software is really for, because it can be very complex physics. Now, for our purpose, because we're not doing anything too crazy, I actually got a very basic version of spherical shapes, rectangular prisms, and a few other shapes on there, and I added it on a sacro file called Commons Properties. So I added the physics for some of these shapes on here, for the inertia values for a cylinder, a sphere, and a box, because these are very basic shapes that can make up pretty much anything else, right? So if you have these, any simulation, I think at this point that we can create, these will take care of it for us. So all you got to do is, in order to use these, is to make sure that in your robot file, you include this file, just like I'm doing here, right? And that would make sure that it's available within your URDF file. And then whenever you go and add the inertia, you have to call it this way, right? You're going to add it. You're going to tell it, what size is it? This is usually something that you'll pull and you'll copy from the actual geometry as well. You can see that. It's not too crazy. And then here you get the same thing that you're doing in the other ones. You're going to have these, you're going to copy from up here. You're going to copy from these values here, which is the origin. That's the orientations. The orientation for the X, Y, and Z values, and the orientation for the rotations. So it's a copy from those. That's where you get that information. It's not, don't overcomplicate it. As long as you copy it this way, if you're using boxes, spheres, or what was the other one, or cylinder, then you should be able to do this perfectly fine. The only value that's extra here is this, and this is the mass. So that's part of physics. If you don't understand how mass works, Google it. But this is going to make a big difference on how your robot operates within simulation. You have to be realistic, because if you change the mass, the robot will behave very differently, right? This is real physics, so you have to be realistic. If you're making a person, you don't want to give it like ridiculous mass, right? Because then it's not going to behave like a human. So you have to, figure out like, what am I building? Okay, then it's got to have somewhere around this type of mass, right? Like this value of mass, so it can behave properly. But if you keep it within yeah, go ahead.
Is the mass value defaulting to kilograms?
Yeah, it's metric systems, kilograms, and any like size, it would be on meters. So if you see this is 0.5, this is 0.5 meters. Or sorry, this is color. So not color, but these, the X, Y, and Z's. Anything like that would be in meters.
Okay.
Anything that's degrees would be radians.
Okay.
Yeah, so when you talk about, spheres, things like that. So so that's what it is. Now, I use a lot of math formulas and stuff like that. Sometimes it's hard to represent numbers. So the good things that we're working with computers, you can literally write a formula and it'll solve it as it executes, right? That's the whole point of simulator. So I use the value pi for a lot of my angles. So pi in degrees is equal to 180 degrees. So if I need to figure out like where to be pointing, half a pi would be 90 degree angle. And, that's the way I kind of work it out. And it works really well, because then you'll get exact measurements, right? You don't do the calculation. You can't divide by pi. You get like a crazy ass number, right? So you just put pi divided by whatever, and it'll solve it for you. It'll be as exact as possible. And that's just a best way to do it. So that's the link. That's half of building a robot. You build a link. Now you're gonna have multiple links, right? You have the base, and then you need to create a wheel now. So let me go ahead and remove this. Well, first you would need two links, right? Two objects, and then you have to have the joint that connects them. That's what a joint is. If you think of a person, right? You have my torso, and then you have my arm. Well, the shoulder will be the joint, right? So that's what this is here. Let me go ahead and remove this one. And we have a base link, and we're going to have a wheel, right? So I'm going to copy the wheel real quick from the left side so I don't have to retype it. I think this would be a little faster. So they said we have the right wheel. We're going to get this one, and we're just going to copy it. We have two links. Now we have, we're building a robot, let's say, because I'm not doing this from scratch. It'll take me too long to type it. But now we have these two links. This link, I'm going to call it, as you can see, I use the word link, but I try to be as specific as possible. Right wheel link, right, to make sure I remember. Going to have the same tags that we talked about. It's going to have a visual. The big difference here is that the geometry here is a cylinder, right? It's not a box. So the cylinder is going to take different parameters. It's not going to have a length, width, and height. This one's going to have a radius and a length. It's a cylinder, right? So you just have to pass it those values. In my case, for the wheel radius, if I go back up here, you're going to see that one of those properties that I created is going to be the wheel radius. Where is that at? Right there. The wheel radius is 1/10 of a meter, right? So let me go ahead and copy this one. Because I'm gonna execute this on Arvis right now so we can see what we have so far. But now we have, where you go? We have this property, and then I'm also using base width and base height, so I'm just gonna copy those two real quick so it doesn't crash on us later on or I forget to copy it. So now now there's no problem if we use those variables anywhere else, right? So we have that like this. We have the wheel radius, the wheel length now. I think we have to copy this too, which is down here. I should have just copied all of them. But we have those variables under. So let's continue with this link. We have the radius and then the length. If you look at a cylinder, right, we have the radius, and then we're going to have the actual length of the wheel. So that's how you determine that. When you look at the origin, it's the same. As you can see, you're going to have different measurements on here. You're going to have the X, Y, and Z, and then you're going to have your rotation, right? So the reason we changed the rotation on the X-axis here is because normally you would get your cylinder facing upwards, and the wheel we need it to be rotated 90 degrees on its axis, right? So that's why I use pi divided by 2. Like I mentioned, pi is 180 degrees, but we're only rotating in 90. That's why I use that measurement of pi divided by 2. So that's why that's there. I created a different material of color gray, which I did not copy. So let's copy that one real quick. We'll copy this here, push it up here for the material set. All right, and then the geometry, right? Now this is a little bit tricky because this is collision, right? This is not the visual stuff. Now, if you guys can see here, I used a sphere instead of a cylinder. The reason I did that is very Gazebo specific. For some reason, Gazebo physics have a harder time when there's friction between surface points, right? So if I were to give it the collision of a cylinder, you guys can see it on the camera, right? I have to like visually explain this just so it can make sense to me. If you have a wheel, let's say this is a wheel and it's rotating this way, right? There's multiple points of contact with the floor, everything across this edge right here, right? So for some reason, that behaves differently as if it was a sphere. If it was a sphere, if you think about a sphere, only one single point on the bottom is going to touch. Very minimal, right? That for some reason translates better to the real world than if you had an actual cylinder simulating on a wheel. Now it's kind of funny, and if you guys would have learned this on your own, you probably would have realized that way later on. Why is my robot moving slower in real life than it's moving? You know, it would have just confused you, right? So this is just something I do, my team does. We learned this from somebody else. I don't know who it was, but it's something that's been very useful to represent wheels with spheres on its collision. So it just computes faster, it works better. So if you guys can think of that, the only thing that needs to be pretty much the same there is the radius, right? The geometry has to match, so it's exactly the same size. We don't want it to look like it's floating in the air or anything like that, because it will detect the collision. But that's why we used a sphere. You know, that way it makes sense to you guys.
That's
Now
gold.
the origin, yeah, I mean it's useful. Like if you would have tried it on your own, and if you guys want to try later on, if you guys have a physical robot.
When would you even realize that? It would take so long for someone normal who's just starting to realize that.
Yeah,
That's
like
really gold.
it's a very big issue going from simulation to the real world and trying to mimic it exactly. So often enough, like you don't know if it's a software related issue. You don't know if it's a mechanical design issue or what it could be, right? A lot of times it's even electronics. Maybe you didn't tune the motors properly or the encoders are failing, right? So this is just something that, like you said, it is gold. It has been for us because it's something that we would have never known if we would have just kept on going with it and try to optimize the other two components versus this, right? So it saved us so much time and effort on our part. So
Beautiful.
that's something you can use. Now, the origin, very similar to the other stuff. It's pretty much a copy. The only thing here for the geometry, since we don't have to rotate the visual of a sphere, because no matter if you rotate it, it's the same thing. That's why we didn't copy it 100% as here, right? The visual, we need to make sure that the visual rotates of the wheel, so we see it rotated. But the sphere, it doesn't matter if we rotate a sphere or not, so that's why that's just 0, 0, 0. Okay, and then once again after that, you have the inertia. I provided that for you guys, so you know you just have to give it a mass and then give it the information that it requires on there. This once again, it gets copied. So this is radius and then the length, right? Because it's a cylinder. So in order to know what that requires, you can open up the commons property, and you're gonna see the properties that it carries over. See, like the parameters and stuff like that. Quick look over this, you can find it. And there's a page that we'll add on the README. I don't have it ready available, but if you really wanted to understand how this works, how this matrix works in physics, there's Wikipedia documentation that's very, very easy to follow. That's what I looked over when I created this for you guys. I actually did the conversions and stuff like that. So I'm probably going to be using this for later on also. All right, so those two are links that are ready to be put together, okay? Why do we need to put together these two things? Is we're going to have to use our joint. So a joint is just a way of telling the simulator, hey, this part needs to be attached to this part in some sort of way. So to do that, we use a joint tag. Joint tag, this one we're using our base link to the right wheel, right? So this is the joint that we're going to do. We're going to just copy this and we're going to paste it. Now, there's no specific order on this as long as the joint's referencing something that has been written before it, right? If I were to have this joint before one of these two tags, then it's not going to know where to grab the information from. So that's the only thing. What I typically like to do is the links need to exist first. So I create all of those. And then after I'm done with the links, then I put all the joints. It's just natural sequence for me. You know, you build the links first and then the joints afterwards.
I think another intuitive way to say that would also, maybe for someone with less tech experience, would be like every component of the system has a parent component. So like a wheel would be attached to an axle, which would be attached to a chassis. So chassis would have to come first, or else what is the axle attached to?
Yeah. So that's exactly, you know, whatever makes sense to you, you just have to make sure that whatever it needs exists already. Otherwise, you know, it can't happen, right? It can't exist. So naming convention, I like to use the word joint, and I like to kind of write out what's being connected. So in this case, it's the base and it's connected to the right wheel, and it's a joint, right? Now, let's see there. Now, another important thing is the type of joint. Now, this is important. There's different types of joints. And let me go ahead and pull up a documentation straight from Ross on here.
Nice.
URDF joint types. Okay. I'm bringing this over here to the screen. Hopefully you guys can see this. All right. This is a very good resource. You can always go back to the ROS documentation. If you put this wiki.ros.org/URDF, you're going to find anything related to URDFs, even stuff that I might not cover right now because it's not necessary. Recommend still go through that. But as far as joints go, there's different types. They have different attributes and things like that. The type, which I just passed up here, where's the type? The type, right? We have these different types right here. We have revolute, which means that it can rotate in a specific angle, right? This is something it's not optimal for a wheel because a wheel would just be a continuous, which is the other type that's right here. A revolute might be if you have a hinge, maybe a door or an elbow, right? That it has a limited range of motion, but it is going to be on an angle. That's going to require to have a specific limit, right? So
as in, like, my arm can't continue from here. So it only can go this far or this far. It can't continue here either. If it was a wheel, it would be continuous. It wouldn't stop rolling.
Yeah. So that's what it is. Revolutes. If you go down here in this same documentation, it'll tell you this element, it's only used on a specific type of joint or something like that. So you guys can look through this, but really brief, like we mentioned, revolute is when there's a limit to the motion on an angle. Continuous is something like a wheel or a fan or something that will continuously rotate on a specific axis. Prismatic, if you're not familiar with the word, is think of it as a plane that just moves back and forth on one axis, right? Fixed would be something like a base, something that's stationary. In this case, the main structure of a robot, it's a fixed structure. It needs a joint sometimes, but it's just going to be fixed. For example, the camera that I added to the body, right? That's not going to rotate. It's not going to move. It's just something that's attached, right? So that would be a joint that's fixed, that's connecting two fixed objects. The floating joints, I don't use too much. It looks like this would be something to be used on a more complex thing where you don't just have X, Y, and Z. It looks like you can have up to 6 degrees of freedom on there. So it might be like a ball bearing type of thing, right? Where you can just rotate like a socket, where you can have like different types of angles of movement. And then a planer, I've actually never used planer before, so I can't give you even a good example for it, but there might be specific use cases where we can use that.
Oh, that must be like for takeoff, maybe like propeller.
I think it might.
Yeah. In the perpendicular to the axis would. Okay, yeah, not always X, Y. Okay.
Yeah. So I'm thinking it might be a way of using prismatic, but on a more restricted manner. Like maybe you can only specify 2 perpendicular axes, or whatever you say, and maybe just not allow anything else. We can look into that. I'm actually gonna look into it because I've never used planer before. If I've used it, I didn't know I was using it. That was probably something that maybe our designer did. But these are the only ones. For our purpose, we're going to work on wheels, so we're going to use a continuous one on there. So I'll go ahead and go back on here so you can see the type it's required. You're going to put continuous. Now, this is going to require these 4 tags within the joint. It requires a parent reference, which means which link is the main one, right, that it stems from. In this case, it's going to be the base link. So you need to make sure that under the link name, you're going to put the actual name that references it, right? So we go back up to our link and it's called base link. So you have to put the parents and then you have to put a child. You have to tell it which is the one that kind of gets connected to that one. In this case, it's going to be the right wheel link, which we have up here. If you mess up on these names, it's going to crash. It'll give you errors. But these type of errors are easy to spot because it'll literally tell you, we can't find this link. And it'll give you the link name. So then you realize like, oh, okay, it's had to do with the way I coded the URDF. So it requires that. Now the origin, this is the origin of the joint, okay? Now this is not the same thing as the origin from the link. This is something that sometimes is confusing for people to figure out. But imagine this, right? You have the wheel, or you have the robot. And if I were to launch the URDF, it'll probably be easier to see. But you have the base of the robot, and then you're going to create a wheel that's going to stem off the robot, right? But you don't want it to start off right at 0, 0. You want that wheel to be slightly off the origin of the main arm, right? To give it more space to clear the bottom of the base. That's where this would take place. That's where the joint happens, right? So
Right.
you guys can kind of play around with this, but that's how it behaves. Don't think about the physical object, but where the actual joint happens, I guess. So another way to do it is if you design a link, let's say you have a lever, right? The lever is not gonna rotate in the middle, right? The angle has to be at one edge, so it rotates up and down. That's where you have to offset that joint position. The origin of the joint's got to be at the edge, not on the center, because it's always going to default to 0, 0, 0. So that's where that would probably make a change. Like if you're going to put something that's going to push your opponent, right? Something that's going to lift them up. That's where you'll probably have to create a link for that arm that you're going to attach to your robot, but the joint's not going to be in the center. You're going to have to offset it on one axis all the way to the edge to make sure that, it rotates at the edge of it. So that's
this
where
would be in order to prevent collision between the corners of the extension and the parent object, correct?
So this has nothing to do with the collision. It's just how it's going to behave on the angle on the joint.
Okay.
You see? Yeah. So that's why it kind of becomes a little bit confusing, because it really has nothing to do with how it's going to behave on the physics, or it does have to do with physics, but it's strange to explain. Yeah, like it's just how the angle is going to work. Like if you have this ruler, right, and you're going to put a revolute axis, right? It's kind of blurry, but if you put this pencil right here in the middle, right, the revolute's going to happen. There's going to be like a propeller. But if you offset that origin to be over here, then it's going to rotate.
Right.
Wider.
Okay. Yeah. I'm glad I clarified. I was thinking that you meant offset away from the actual object. Okay.
Yeah. So it's just a joint. Like if you're going to put revolute and it's at 0, 0, 0, it's going to rotate like a propeller. But if you put it over here, you offset at that joint, then now it's going to rotate this way like this.
Mm-hmm.
So that's where that comes into play. And then the last one is the axis. This is which way is it rotating and which axis is it rotating. So the value doesn't really mean anything. It's either a 0 or a 1. So in this case, if it's a wheel, on which axis is it gonna be continuous rotation on? It's gonna rotate in the y-axis right now. So if we put this 0 and we put a 1 on the x value, then it's gonna rotate now on the x-axis. Does that make sense?
Yeah.
Okay. So
like if you had a wheel that was pointing in the y-axis and you rotated in the x-axis, you'd have a wheel that was spinning like this, right? Like
yeah, like a coin, like a flip of a coin, right? So you want it to rotate. Yeah, so that's what that is. And these three components, or two components actually, the link and the join, are all that's necessary to really visualize a URDF.
Wow.
Anything else after that, it's additional things that you can add that are not specific to the URDF per se, but it's like plugins, like for example, the control system, right? If you guys look over here on the left side, I have a few more includes. These includes right here just allow it to not to look messy, right? So like this mobile-based Gazebo is something I provided for you guys as well, which opened up here. This is a bunch of stuff that's Gazebo specific. It opens up system resources. Like this is what that works with the control, with the differential drive, all those kind of things. So this is stuff that's not specific to the URDF. It's stuff that can be added to the URDF, so it works well with Gazebo. There's other simulators like PyBullet and a few other ones that have their own type of tags that you would add when you work with those simulators. So this is not something that's specific to creating the URDF. It's specific to Gazebo to be able to take advantage of some of the features, like the controls and stuff like that. So I'm not going to go over this specifically, but there's resources inside the wiki there on the top, Sacro. You can find out a lot about these specific things. But just so you know, this is what allows us to use that teleoperation script to move things up and down. And if you study it, it's not that confusing. Everything's kind of, it makes sense when you read it, what it does, right? Very easy. If you ever use this command and you like kind of copy and paste it, as long as you know the joints that hold the wheels, you can use this control system. So all it takes is these two tags to tell it those are the joints that control the wheels. And as long as the right axis and everything are configured in the URDF file, it would work. It would operate. So you can literally copy this into any other two-wheel robot and it'll work. It should be a copy and paste type of thing for you. So that's what that is. Now, let's say you already designed your entire thing, right? You have the whole file. We're just gonna save this, and we're not gonna see the full robot, but we at least have a base and we have one wheel that's gonna be attached to it. From there, you keep on doing the same thing to add another wheel. You might just have to reverse the axis, maybe the positioning a little bit, but it's just a configuration thing. There's not really much to it. You know, adding any other shape, you just do it the same way. It's not that difficult. So let's go ahead and save this real quick. I'll just save
would
as.
would I have to keep saving and rebuilding? There's not a way to like do a hot reload?
For the Sacro files, I don't think you have to source and do all that kind of stuff. You can test it. Since it's not a package specific thing, I think it's just one of the file resources in there. It's an XML file. It's not it's actual code. You know what I mean? When the code runs, it pulls that file. So I don't think you have to be doing a Qualcomm build. Test it just either way. I don't build URDF files all the time. But I don't think you would need to because it's not something that gets built every time you do Qualcomm build. It's just a resource file, right? Okay. But to be able to visualize the changes, though, you do have to be launching Arvis every single time you update the file. That's something you can get away with. If you get more experience and you want to use CAD designs or CAD software, like anything out there like Fusion 360 stuff like that, they allow you to export into URDF, so you can probably get away with a lot of the design there and just make minor modifications when you export. I'm not like an expert at CAD design. I can design things, but that's not what my focus work is. So, but they do it. I've seen them do it. They have their ways of speeding things up. So you can try that. Now, I know you probably built packages already because you're following that other tutorial. So just keep in mind that the file has to go into a package, right? Yeah. So this package is called my robot description. So when you build a package, there's a command that you follow in ROS to build a package and stuff like that. It can either be a Python package or a C++ package. In this case, I went with the C++ because it didn't make a difference which one you use for this type of thing. When it's a description, a URDF, the package is very minimal. Doesn't really utilize everything that a package would allow you to do. But you do have to build a package, and in there, that's where you'll create the URDF folder, and inside the URDF folder of the package, that's where you'll put the Sacro file. That's if you look at the directory structure on my left side, that's why I have the package name, and there I have a URDF, and you see the CMake list.txt and the package XML, the stuff that was created for me automatically when I built the package. All right, so I'll call this one, I don't know, we'll call it test.urdf.sacro. I'll tell you this is my naming convention. I don't have to put URDF under. The way I like to do is this. If you can see some of my files, they say only Sacro, and then some of them say URDF. My main robot, I always put .urdf.sacro. That's how when I have like 20 files in there, I know that the main file that everything stems to, is the one that has the URDF name on there. Everything else, as you can see, there's an ARM one that doesn't have URDF. There's a camera one that doesn't have. That's because those are attachments. They're going to be added or included into my main URDF. That's just what I do. It makes things easier for me at a glance to look at it and not have to be like, man, they're all start about the same or whatever. So you guys can find your own way, but that's what I do. So since this one's going to be like a brand new robot, I'm going to call it this way.
Do they all have to be under the URDF folder, or can we create subfolders?
Within the URDF, you can create subfolders. You just have to make sure that you include that on the file path. It's like a relative path when you include it in there. So like there's robots that have like so many moving parts that you have to put subdirectories, because if not, you'll have your list would be like so crazy, right? So you can just follow your own structure on there. So test.urdf.sacro, I'll save it. So now that we have that file on there, then we're gonna use that other command, but instead of launching the my robot URDF, we're gonna give it the test one, and we should see a robot pop up on Arvis. So I'll go here. It's this last command that we did, but the file that we're gonna run is test urdf.sacro. So when I launch this, if I didn't miss anything, it should open up that robot, and it did something. What does it say? Macro name, box inertia. So I guess I didn't include the inertia file or something in there because it cannot find the inertia box in there. So since I was copying and pasting, I probably forgot to include those files on there. So I'm using the inertias for the box and all that. And yeah, I did not include that commons properties file in there. So that's why it crashed. So I'll go back in here, and it's this specific one. So I'll copy this. I'll put it under my materials. So now it should work. And sorry about that. And we do this, we run it, then I know the inertia. And as you can see, that's what we built so far.
Okay.
Now, if
So
we make
simple.
a modification, you reload it.
It's so simple, and the possibilities are so endless. You can do anything with
Yeah.
with.
And it's-
Okay, so I see that yellow line is there. That's the joint that's connecting them, right? Yeah. Okay.
Yeah,
Understood.
that points the child to the parent joints, right? So
Yeah.
the parent's always the one it's pointing to. Yeah, so that's how you visualize it. And if it gets too messy, here on the left side of Arvis is a visualization tool. It doesn't really do anything but allow you to see what you have on your robot description. So the transforms, right? Once you get more into creating URDFs and things like that, or the joints, how things behave with each other. So if you look at the frames, you have a right wheel, you can remove that so you don't want to see it. If it gets too messy and you only want to see the base length, or you're like, why is that behaving incorrectly, right? You can see that. You can kind of do that. And then there's a bunch of other stuff like the base link. It tells you what, this is a tree, like what's connected to what. That's just allows you to see what's dependent on what. So you can study all this stuff on here. The robot model, you can hide actual structures. So you can hide them. Where is it? Under links. If you don't want to see the base link, you can just hide it. If you don't want to see the wheels, you can hide the wheels. This is your tool to visualize all this kind of stuff.
Okay, that's just if you have like smaller components and stuff. Oh, okay, you can do the rotation right there. All right, that's interesting.
Yeah, this is part of the package that we downloaded it with those two apt install commands that I gave you. The ones that you install last, that allows this to open up. This is something that if you didn't use those packages though, it's something that the joint state publisher, this is something that comes with the ROS. You just have to know how to visualize and create this screen on there. But the package that I gave you, it makes it very easy. It's what we all use because it allows you to test your joints. So if we had a prismatic one, it wouldn't rotate, but it'll move around the axis that you told it to. So you can test all the joints and everything with this. So if you add a second wheel, automatically it'll add it here for you and you can test it. So that's the cool thing about this package. But yeah, the call went a lot longer than I thought, but I think we took a lot longer at the beginning trying to set up the existing world. I think this went pretty quickly once we just copied and pasted and I kind of dissected this a little bit. So
no, but this
yeah,
is a lot. This is good though. Thank you.
I'll be splitting this into 2 videos for sure.
Yeah, that's what I was gonna say. I think in the future,
maybe 3.
We need to figure out how to shorten these talks.
No, I actually prefer the long sessions. Well, if we're gonna be doing it weekly,
yeah, I like that. Like and I can separate it later. The only thing is, it might make it harder for people to stay on. Is the only thing that I'm worried about.
Yeah, because of time, right? Like everybody's trying to make time and everything. I saw
almost
2 people jump off.
Yeah.
That sounds like a Zen problem. I don't care.
Honestly, I'm like that too, man. I'm 100% like that. And I have no problem if we're going to be recording these and it goes 3 hours and we have a bunch of people in the first hour, we'll just do the rest of it ourselves. The people can watch the video. I don't have any problem with that.
No, if we're going to be doing it weekly like this, and if we have it shorter, that makes sense.
For sure.
Yeah.
But like if I have to wait 3 weeks just to finish the one conversation, that's going to stress me out.
Yeah, true. I think if it takes too long, whenever I follow some sort of class or something that's structured, I don't like to stay in between either because I tend to forget stuff like, why was I doing that or something, right? Especially when I'm following instructions. So in those scenarios, I like to follow through with it all the way. I cannot leave too much time in between. But like you said, people fall off of the meeting because they have other responsibilities or other things, other commitments. So something like this maybe could be broken up into two. The first one, setting it up, downloading the packages, fixing issues like with the stuff that we were doing the last couple of days, right? Making sure that everybody can load the simulation and everybody's ready to go. And maybe the second one can be like, okay, now that you have the packages, and then this second part, let's open it up. Maybe we would have had enough time to actually build the whole thing, which doesn't need much more, right? The other one is going to be a copy of this Revolut link and the joint. And then the other one's going to be a fixed sphere in the front, right? So I'm sure by what I explained, you can do it, right? It's not that complicated anymore. But maybe we could have done that way. Maybe we have to kind of plan it out differently next time.
And not all of we we're going to be meeting every Friday. We don't have to only meet every Friday. We could tell people meet up Thursday to set up your environment. If you feel comfortable doing that yourself, do it yourself. And on Friday, we're going to get right into it. Something like that.
Yeah, like maybe send the commands or the instructions with screenshots of what they should see prior, right? And then I don't know, something like that. But we can try different things, see what works best.
This meeting, it has been 3.5 hours, but it's 3.5 hours of pure gold. I'll definitely separate this, put it in our playlist, because this is everything we went over here, 100% important.
Yeah. Did you record the first hour? Because we logged in an hour earlier.
So I have two. I see that Livy has been recording for almost 3.5 hours. I recorded our conversation before the meeting started. And then I had a separate recording that's probably about 2 hours long at this point of the actual.
Can I stop recording actually?
Yeah, I think so.
Yeah.
Okay, no, so the whole video link of recording, like from when you started, was 2 hours.